Hi, welcome. We'll start in around 8 minutes. I'm just putting up the paper we are going to discuss. I'm putting in the chat the link to our guest speaker that will be talking, Abbigail Elms. She's at Warwick University and a really great physicist who will be talking about her really interesting research of ultra cool white dwarfs. I think it's the second coolest white dwarf ever recorded. So it's really interesting. And the characteristics of that white dwarf will be discussed. So yeah, if you think this is interesting, feel free to share the room. Our guest speaker should be arriving in a few minutes. So thank you. I will be switching the link on top of the room to the PowerPoint presentation that our guest speaker prepared for today, and I'll put this link for the paper in the chat. Um, so um, I hope this file is not too big. Let me know if that's the case. And Hi, Solomon. How are you?
I am fine. What about you, Katrina?
Good, good. Thank you. We will start in 2 minutes. I just put the PowerPoint presentation up and I will put the paper that we will be discussing, and it's open source, in the chat. So,
Okay, sure.
and yeah, our guest speaker will give a talk, and then after the talk, we'll have time for questions. So, yeah, I'm looking forward to it.
hmm What topic you were discussing?
Our guest speaker, she's a physicist, and she will talk about the. Hi, Abigail. How are you? About the very cool white dwarfs. So I will mute you now because now, or if you want to mute yourself, thank you. Hi, Abigail. How are you? Can you hear us, Abigail? You're muted, so I'm not sure. I'm not sure if you can hear us. Um,
Oh, there we go. Can you hear me
there.
now?
Yes, now we
Okay.
can hear you. How are you today?
I'm fine, thank you. How are you?
Good, thank you. I posted the PowerPoint version because I think it works.
Okay,
So
fantastic.
yeah, so we have some animations, and we'll start in a minute. So for everyone, I posted in the chat the link to our guest speaker's website. There's more information about her, and then the second link is the link to the paper, and it should be open source, so everyone should be able to access it. And on top is pinned the presentation link that also everyone should be able to access it. If not, please let us know. And I'll just share on Twitter really quick, if you have a second, that we are about to start. And then we'll start. Okay, perfect. So I know people will keep coming in, but I think we can slowly start and go from there. So welcome everyone to Science Society, and a special welcome to Abigail. And before we start, let me give you a little bit of an introduction so you get to know her a little bit. Abbigail Elms, she has a master in physics, and she is a PhD student in astronomy and astrophysics group at the University of Warwick. And her supervisor is Pierre-Emmanuel Tremblay, and her research focuses on studying white dwarfs within the Milky Way galaxy. And she uses photometric data and spectroscopy data from the Very Large Telescope, but she will probably talk more about that, so that I don't want to give too much away from her current research. But she already published really significant papers, and she also has other research interests in galaxies, black holes, and general relativity. And for her master's research project, she identified dwarf galaxies in SDSS MANGA, I hope I'm saying that right, data, and determined which of them likely hosts an active galactic nucleus. And then she discovered each dwarf galaxy's local environment to see if there's a correlation between this and hosting an AGN, which is the active galactic nucleus. She taught and did already a lot of outreach during her 4 years at the University of Portsmouth. And she was part of the Physics Society and was president in her second year of that Physics Society. And she also, in addition to being enthusiastic and about physics, she has also played competitive netball for 15 years at the university and country level. That's amazing.
Thank you.
So usually before we start, we ask a few interview questions, if that's okay with you. And the first one would be, how did you discover this passion for physics? Was it something you always had, or did it start with a class or a book you read? Because obviously you're very passionate and good at it too. So, yeah.
Yeah, no problem. So I didn't always know that I had a passion for physics until I really started to get into it in high school for GCSE and A level, and I found out that I really enjoyed maths and physics together. And physics was a fun way of applying maths, which really appealed to me. And we did an astrophysics module in school for our A level, and I totally fell in love with space and studying the stars and our galaxy. So yeah, from there I never looked back.
Well, wonderful. I'm glad you did. And and for this specific project, is there maybe a background story about, why you chose this research field and then choose to work in this specific project? Was it like hard in the beginning? Was it easy also to get the data and collaborate? Yeah, thank you.
So I initially chose this project out of a sample which were pitched to me when I started my PhD. And I mainly chose it because it was a massive puzzle that no one had any idea about. We didn't know what we were going to find, and it was completely starting from scratch. So we just had some data, no one had looked at it yet. So it was a really exciting project to start with. So that's why I chose it. And it was not easy, like all science, I would say. All science comes with its challenges. But it's super rewarding when you figure things out and your code works and you get results. So because it was such a puzzle to begin with, that's why I think it has been so rewarding getting these results out.
Well, that's wonderful. I mean, it must be really rewarding, but also congratulations for your persistence. I think that it most likely you needed to have that character trait to start something from scratch. So yeah, congratulations on the publication.
Thank you.
And yeah, and yeah, we are really looking forward for your presentation. So everyone should be able to access the link, and the stage is yours. Thank you.
Okay, fantastic. So yeah, if everyone can access the link and look at the presentation, that would be great. So yeah, hi everyone. Thank you, Katerina, for that great introduction. And thank you so much for inviting me to speak to you all today. So as already mentioned, my name's Abby, and I'm currently completing a PhD at the University of Warwick in the UK. And my research focuses specifically on white dwarfs and their evolved planetary systems. which is the title of my talk today. So let's get started, and let's go to slide 1. So I've numbered my slides to hopefully make it easier for everyone to follow along. So let's begin with just asking ourselves, what is a white dwarf? And this is the fundamental question of this talk. So if you only take away one thing today, I hope this will be it. So if we go on to the second slide. So what is a white dwarf? It's basically one of the remnants we can get from stellar evolution. And here is a diagram of the stellar evolution of low and medium mass stars, including the Sun, on the top branch, and the evolution of high mass stars are on the lower branch. And all stars are formed the same way from a cloud of gas and dust called a nebula. And then they evolve to the main sequence stage once they start fusing hydrogen into helium in their cores. And stars spend the majority of their lives on the main sequence, and the amount of time they're on depends mainly on their mass. So high mass stars evolve quickly as they burn through their hydrogen fuel at a faster rate than lower mass stars. Then they evolve into a red supergiant and then violently explode as a supernova, which expels all its outer material into space. And with high mass stars, this just leaves a very dense and fast rotating remnant behind, which is called a neutron star. Whereas very high mass stars, which have an initial mass approximately greater than 40 solar masses, so that's 40 times the mass of our Sun, these will eventually turn into a black hole. And for my research and this talk, we're interested in the top branch of this diagram, which outlines the stellar evolution of low and medium mass stars. And these stars will live as a main sequence star for most of their lives while they fuse hydrogen into helium in their cores. Then, once this fuel runs out, they will become unstable and contract due to gravity. And this causes the star's temperature to increase. So it will begin to fuse any hydrogen which is outside of the core in a shell surrounding the core. And this causes the star's outer layers to expand in radius and cool as they are further away from the core. And this results in the star becoming redder in appearance. And eventually, all the fuel in the shells surrounding the core will be used up, and the outer layers of the star will be ejected as a planetary nebula. And all that's left of the star is its core, which is what we call a white dwarf. And approximately 97% of all stars in our galaxy will become white dwarfs, including our Sun. So they are very common, which is why it's important for us to understand them. And if we go on to the next slide, which is labelled slide 3, we can see a Hertzsprung-Russell diagram, which basically shows the different phases of stellar evolution related by the temperature and luminosity of the stars. And this is a slide with an animation on. So if you click the spacebar or arrow or whatever you click to make the presentation go to the next slide, you should be able to see a star going along the red track that is outlined on top of the diagram. And this red track is a typical evolutionary track of a low to intermediate mass star like our Sun. So it shows how it evolves over its lifetime from a main sequence star up to the red giant phase, and then its decrease in luminosity and temperature when it becomes a white dwarf. So if we go on to the next slide, which is labeled slide 4, we'll talk a little bit about what a white dwarf is like. So a white dwarf is the leftover core of a low to intermediate mass star. They are extremely dense as they have a mass approximately equal to 1 solar mass. So that is the mass of our sun. But they have a radius comparable to the Earth. So they have got a mass the same as our sun, but all of that is condensed and squished down to the same volume of the Earth. So their cores are usually composed of carbon and oxygen, and they're degenerate, which means they're only supported by electron degeneracy pressure. So the matter in the core is packed in as tightly as it possibly can be, which is why they're so dense. The white dwarf core is surrounded by a thin envelope of residual hydrogen and helium left over from the star's post main sequence evolution, and this is what makes up the white dwarf atmosphere. And the core of a white dwarf is very hot when it first forms, which is probably no surprise, seeing as it was just a star. And the degenerate matter makes it almost isothermal, which means it almost stays at the same temperature. However, throughout the white dwarf's lives, they do gradually cool as they radiate their residual thermal energy away throughout their non-degenerate envelopes. So they basically just lose their thermal energy, their heat, extremely slowly over millions and millions and possibly even billions in some cases of years. So the large surface gravities of white dwarfs cause this atmospheric purity of hydrogen and helium. As the heavier an element is, the faster it sinks through the white dwarf atmosphere and onto the core. Therefore, we should only see hydrogen and or helium present in a white dwarf atmosphere. But if we go on to the slide labeled number 5, we can see that 25 to 50% of white dwarfs have an evolved planetary system, which can accrete onto the pristine white dwarf atmosphere and pollute it with elements other than hydrogen and helium. So, how exactly does this happen? So if we go on to the next slide, which is labeled slide 6, we can rewind back to our stellar evolution of low and intermediate mass stars. So we can use the sun and our planetary system as an example, and we can see how it affects the planets. So the sun evolves off the main sequence into the red giant phase and therefore expands, which is shown at the center of this diagram. And the inner rocky planets are Mercury, Venus, Earth, and Mars. And we know when the sun expands, it will definitely engulf Mercury and Venus and possibly Earth, but Mars is likely to survive along with the outer planets. And as a result of the sun's expansion, the surviving planets will be forced out onto larger orbits, which we can see if we go on to the next slide, which is labeled slide 7. And we can see that the planets will be forced onto larger orbits of approximately twice the radius of what they're currently on. And then the sun will evolve into a white dwarf, which is the tiny little white circle that is in the middle of the diagram. Because if we remember, a white dwarf has a radius comparable to the Earth. So it's the same size as the Earth, so it's tiny. Okay, so due to the really high gravity of a white dwarf, this tidally disrupts the surviving planetary system, and it can break apart the bodies into planetary debris and planetesimals. Planetesimals are just very small planets and bits of planets that have been broken up. And this material is then left to orbit the white dwarf, and it forms something called an accretion disk around it, which can spiral onto the white dwarf atmosphere and pollute it. So if we go on to the next slide, which is labeled slide 8, we can see that when this happens, we call the white dwarf metal-polluted. So when an astronomer or astrophysicist says the word metal, we are referring to any element heavier than helium, which is a little bit different to the classic definition of metal, but just go with me here. So we classify these metal-polluted stars as something called DZ. So if you ever see someone call something a DZ, white dwarf, that means their atmospheres are polluted by metals. And we basically know this because they show metal lines in their spectra, which I'll talk a little bit more about later on. And the high surface gravity of white dwarfs cause the metals to sink below the atmosphere on short time scales, where the heavier the element, the faster it sinks. So when we discover a metal-polluted white dwarf, we know it's either actively accreting or it recently accreted the material. If we go on to the next slide now, which is labelled slide 9, we can see that we can work out the composition of the planetary debris which accreted onto the white dwarf using spectroscopy. So basically we can observe our white dwarfs using a telescope on Earth here on the ground, and we take something called spectroscopic observations of it. And this basically lets us obtain its spectra, which is a collection of its light over a certain wavelength range. And this tells us what elements are in the white dwarf atmosphere. So it's a pretty cool and useful technique and observations that we can take. So then we can use computer models to determine the chemical abundances, which we can compare to known bodies in our solar system. And we generally compare to Earth, as it's the most useful comparison for obvious reasons. So we've got two pie charts shown here of the chemical compositions of bulk Earth and the Earth's continental crust. Bulk Earth is just what the whole Earth is made up from. And so it's basically just mainly iron and oxygen with some silicon, magnesium, and some small fraction of other elements. Then the right-hand pie chart shows the differentiation of the Earth's continental crust composition, which is mainly oxygen and silicon, with some aluminium, iron, and magnesium in there, then some small amounts of calcium, potassium, sodium, and other elements. So these are all the main metals we look for in metal-polluted white dwarfs. Then we can compare the abundance ratios we find with those found in these solar system bodies that we find. So, for example, bulk Earth and continental crust. So, if we move on to slide 10, we can move on to this study that I conducted the research for. So that was an overview of white dwarfs and their evolved planetary systems. So now we can move on to talking about my research in particular. So the study I've just completed with my collaborators, who are listed here, is called Spectral Analysis of Ultracool White Dwarfs Polluted by Planetary Debris. And we have an exciting result from this research, as we have confirmed the oldest evolved planetary system around a white dwarf in our galaxy, as we found the oldest white dwarf that is accreting debris from orbiting planetesimals. So, if we go on to the next slide, please, which is labeled slide 11. We can see here an artwork which was made for our press release of our study. So I just think this is a useful visualization to keep in your heads, as we found 2 white dwarfs polluted by planetary debris, which is helpfully portrayed by the rocks here on the left-hand side. And from the 2 white dwarfs that we found, one is unusually blue and one is very faint and red. So for the remainder of this talk, when I'm talking about this research, this is a good picture to keep in your heads, just so that we don't get lost along the way. So, if we move on to the next slide, please, which is labeled slide 12. This is, well, first of all, let's start at the beginning of how we first started researching these stars. So, both white dwarfs were identified as high confidence white dwarf candidates in a large catalogue of stars identified by the spacecraft Gaia. And it was noticed that both white dwarfs have unusual colours and brightnesses compared to other white dwarfs identified by Gaia. And they were flagged as being potentially very cool. And when I say very cool, that means in temperature wise, as in cold, not as in cool as in like you're cool, which we get with every talk that we do. So then we plotted our 2 white dwarfs on a Hertzsprung-Russell diagram, which is shown on this slide. And the coloured dots on the plot show the white dwarfs identified by Gaia within 100 parsecs and the SDSS footprint, and they're coloured depending on their spectral types. So here we're only interested in the metal-polluted DZ white dwarfs, which are the blue dots. And we basically wanted to see if these 2 white dwarfs were different to other DZ white dwarfs of similar temperatures with detections of lithium or potassium. So we identified a subsample which we boxed on the diagram with red open markers. And you can see straight away that WD J2147 minus 4035, which is enclosed with the diamond marker, is very faint and red compared to all the other white dwarfs, not just in the subsample. So that white dwarf is the one that is in the bottom right-hand corner of the plot with the diamond red marker surrounding it. So that is quite a way off from the white dwarfs in general and from our subsample. And the other white dwarf in this study, which is WD J1922+0233, and that's enclosed with the red circle, which is sort of in the central region of the plot, but maybe in the lower third. And this is in an unusual position compared to the subsample, but also for a general DZ, as there aren't any other blue dots surrounding it in this plot. So that's quite interesting. as this is what we call an infrared faint white dwarf, as it has an unusual blue colour for its temperature, because its flux is being suppressed in the red optical and infrared bands. So, if we move on to the next slide, please, which is labelled slide 13. So, using that diagram on the previous slide, we established that these white dwarfs are in fact unusual, like we thought. So my team observed them using the X-shooter instrument on the Very Large Telescope, or the VLT, in Chile, and obtained spectra for both of these white dwarfs, which is shown on the plot in this slide. And this is also the first ever spectra taken of WD J2147, which in itself is very exciting. And we can see that both white dwarfs are metal polluted, with a tentative carbon detection in WD J2147. However, further observations are needed to confirm this. And we then used our state-of-the-art model atmosphere code with microphysics improvements specifically tailored for cool white dwarfs to measure the abundance of these detected metals, as then this will tell us about the evolved planetary systems around these white dwarfs. So if we go on to the next slide, please, which is labelled slide 14. We show here zoom-ins of the plots of the metal detections in each white dwarf from their spectra, which were shown in the previous slide. And the red lines overlaid on the spectra are our model spectra, which have a reasonable agreement to the observations and gave us the metal abundances present in the atmosphere of each white dwarf. So we detected lithium, sodium and potassium in WD J2147 and calcium, sodium and potassium in WD J1922. And we also identified that the lithium spectral line in WD J2147 is split into 3 components, which tells us that this star is magnetic, which is also very interesting. So if we go on to the next slide, please, which is labelled slide 15. So we were then able to perform full iterative fits using spectroscopy and the full photometric data sets of each white dwarf to produce synthetic spectra and monochromatic fluxes from our model atmosphere code. So the monochromatic fluxes are the red lines in these plots. Our synthetic spectra are the black dots, and the observed photometry are the coloured dots, and from each survey is shown in the legend with the colours. And these give reasonable agreement to the observations, and by using this technique, this gave us each white dwarf's atmospheric parameters of temperature, surface gravity, cooling gauge, and atmospheric chemical abundances, which I've put in the top right-hand corner of each plot for each white dwarf. So the first line, the log H over He, is the hydrogen to helium ratio in the atmosphere. Log G is the surface gravity of the white dwarf. TF is T effective, which is the effective temperature of the white dwarf. And the Greek letter tau, which is the last line, is the cooling gauge. So that tells us how long the star has been cooling as a white dwarf for. So we can see here that the temperatures for both white dwarfs are below 4,000 Kelvin. So we can call these ultra cool white dwarfs. And both white dwarfs are old, with WD J1922 having a cooling gauge of approximately 9 gigayears, and WD J2147 having a cooling age of approximately 10.2 gigayears, which is the largest known for a DZ white dwarf. And a gigayear, by the way, is a billion years. So if we move on to the next slide, please, which is slide 16. So now that we know the chemical abundances of the metals in each white dwarf atmosphere, we can compare them to solar system benchmarks. So these two plots show the ratio of lithium to sodium against calcium to sodium on the left and against potassium to sodium on the right of our two white dwarfs in this study, which are the purple and blue points, with the grey tracks coming off them. And these are shown alongside the other DZ subsample objects, which we're not too bothered about here, and the solar system benchmarks of the Earth's continental crust, bulk-Earth, solar, and CI chondrites. So the coloured markers show the current atmospheric chemical abundances in the white dwarfs now, and we can see that the current abundances are exotic compared to benchmarks, which is interesting. And we can assume that accretion has stopped, so we can use these plots to work out the chemical composition of planetary debris which accreted onto the white dwarfs from their evolved planetary systems. And we can do this basically by using diffusion timescales, which are shown with the grey lines coming from our two white dwarfs on the plots. And these tell us how fast each metal sinks through the white dwarf. So you can read the diffusion timescales, which are the grey tracks, basically from the coloured marker going to the right. And this is a good technique to use when we can't explain the current atmospheric chemical composition of the white dwarfs, because we can look back in time at the past abundances in each white dwarf atmosphere to see if we can explain their composition using solar system benchmarks at some point in the past. So if we go on to the next slide, please, which is labelled slide 17. We can dive a bit further into this analysis, and let's look at WD J2147 first, which is the oldest DZ white dwarf that we found in our galaxy. And it clearly has an exotic composition currently. However, its composition gets even more weird the further back in time we go, so the further along this grey track we go. So it's currently lithium and potassium rich compared to the benchmarks, and as we look back in time, it reduces in lithium, which is more like the benchmarks, but it gets really potassium rich, which is currently unexplainable. We considered a few scenarios which could explain the composition of WD J2147, including primordial lithium enhancement and the accretion of crust-like debris a very long time ago, but we are not convinced that any of these can adequately explain the abundances. A possible scenario which we didn't explore is multiple accretion events, so that is certainly a task for future research. And now if we look at WD J1922, which is the blue marker on the plots, we can conclude that it's likely that a planetary body with a similar composition to Earth's continental crust accreted onto it approximately 4 to 15 megayears ago. And this is more likely than debris with a composition similar to bulk Earth accreting onto it, because it would have been an earlier accretion event. Therefore, a smaller planetary body would have been accreted, which is more likely. And also, if we take a look at the right-hand plot, The potassium abundance approaches Earth crust when looking back in time, which it doesn't for ball curve. So we can't explain the potassium abundance with ball curve here. So if we move on to the next slide, please, which is slide numbered 18. We can calculate the minimum accreted parent body mass for both white dwarfs depending when accretion stopped by summing up the masses of the individual metals detected in the white dwarf atmosphere and common metals detected in DZ white dwarfs, which are assumed to be there, but have sunk through the atmosphere basically and become undetectable by the time of our observations. And we couldn't constrain when accretion stopped for our chemical abundance analysis of WD J2147 because it's so weird. So we can say that the accreted parent body mass is between the mass of metals found currently and a sensible upper limit of the Earth mass, as a Jupiter or Neptune mass body is very unlikely to have been accreted, and the metals in the atmosphere basically aren't consistent with ice or gas giant planets anyway. And on the other hand, we could constrain that debris with a composition similar to the Earth's continental crust accreted onto WD J1922 approximately 4 to 15 mega years ago. So if we look at the right-hand plot, we can look on the x-axis for time since accretion and go to 4 and 15 mega years, and then go up to the black dotted line and read the accreted minimum mass off the y-axis to give a minimum accreted parent body mass of between 3 orders of magnitude less than Janus mass, and Janus is one of Saturn's moons, to a Janus mass, which is a sensible mass range for accreted debris from an evolved planetary system. So if we move on to the penultimate slide, which is labelled slide 19, this brings me almost to the end of my talk, but I would lastly like to draw your attention to why this study is important. So as discussed, white dwarfs are the most common type of stellar remnant, as 97% of all stars in our galaxy will end their lives as one. And cool white dwarfs are the remnants of the oldest stars in our galaxy, so are fantastic tools in studying what the Milky Way was like in the past. And these white dwarfs in particular in my study give us information on our galaxy's evolution, the oldest stars in our galactic neighborhood, and early planetary formation. And they're an important piece in the puzzle in understanding the Milky Way, as they shed light on what our galaxy was like in the past, as we have identified evolved planetary systems that are approximately 9 and 10 billion years old, which therefore formed and died way before the solar system and therefore Earth was even formed. So if we go on to the last slide now, which is labelled slide 20, I'll leave you here with my summary slide, as I've gone over the half an hour, and I'm happy to answer any questions that you have, and thank you for listening to my talk.
Well, thank you so much, Abigail. Sorry, I had to switch back from the slides to back to the doc.
That's okay.
I couldn't unmute. Yeah, thank you so much for this wonderful talk and for guiding us through, the importance, the evolution of white dwarfs to your current research. It's so impressive. And like a question I had in my mind that is probably, please let me know if it goes too far away from your research or the presentation, but you mentioned like that there's different variety of basically molecules that you find in these type of white, or this very old, or the oldest white dwarf probably you detected. Like, does this difference has to do with the exact time point they turned into a white dwarf? And what can we predict based on this data if this white dwarf solar system had life or not? Like, how likely is diversity of different chemicals, basically, does it hint towards less likelihood, more likelihood of generating life, maybe? And maybe it's way too far away from your research. Thank you.
No worries. Thank you for that question. That is really interesting and a great question. So in regards to life in these evolved planetary systems, I have no idea. But we can basically try to figure out if the evolved planetary systems, so the planets basically that were around the stars, which then became the white dwarfs, we can figure out if they were Earth-like, which is why we tend to try and find, we try to model our model atmospheres with the elements that we find on Earth, like in bulk Earth and the continental crust. So just by doing this, we can then compare the evolved planetary systems that we find around these white dwarfs with the continental crust or bulk Earth, and then the technique that we use with the diffusion timescales by looking back in time. That's basically a way that we can see what if the evolved planetary systems were like the Earth at some point in the past. Because, like I said, the white dwarfs have such high surface gravities, so basically all the elements just sink so fast in a white dwarf that that we can basically extrapolate backwards in time to see what the planetary debris was like. So I wouldn't be able to comment if there was life or not, but the purpose of this study is basically to try to find out a little bit more about what our galaxy was like in the past, and try to find out what sort of material was present. So because the one white dwarf, WD J1922, because that evolved planetary system is has a similar composition to the Earth's continental crust, it hints at us that 9 billion years ago, when that planetary system was formed and eventually died, that our galaxy had the material similar to the Earth's continental crust, which is just incredible to think about, seeing as that evolved planetary system was formed and destroyed way, way, way before the Earth was even formed. So that's interesting in itself. And then with the other white dwarf, WD J2147, which is 1 billion years older than the other white dwarf, that evolved planetary system is completely mysterious. It's weird. We can't explain the composition currently. There's a few theories flying about currently, but there is nothing concrete. So what our galaxy was like 10 billion years ago is still a mystery and needs to be explored some more.
Thank you. Yeah, that's so interesting. That with your work we'll probably know more. And then So the other thing that probably is way too far away, or can you with your data also measure the chirality? Because there's isn't there in physics, as far as I understand, this puzzle why everything is basically left-handed, and interestingly also in proteins of living organisms. Most of like everything is usually left-handed, and when you switch them to right-handed, you can have the exact same composition, just right-handed, and it's something from a helpful drug to a totally toxic chemical that will kill that organism. So is there also like research being done in, or can the data, like how you collect the data, can this be also detected?
That's an interesting question, and the honest answer is I don't know. But it's definitely something worth thinking about.
Well, thank you so much. And I see that Joyce and Praveen, welcome to the stage. Please ask your question. Thank you.
Yes, hi Abigail. That's all very interesting. It's it's a little beyond me as a biologist, but I was interested in the life question, and I also thinking about the Milky Way. I just wish I could see the Milky Way like I did when I was growing up and we were traveling across the country. Uh, and I did take astronomy a long time ago. So anyway, I'm still trying to think of how I can ask an intelligent question about this because it is kind of beyond me. But anyway, I just appreciate it. I'll let Praveen go ahead.
Hi, thank you. Hi, Abigail. I just wanted to ask ask two questions actually. When you say about stellar evolution, can we detect a star becoming a giant red? The second question is that uh, when in the nebula planetary nebula stage, what happened to the existing planet when it become a white dwarf?
What happens to the existing planets? So, in the red giant phase, the planets that are extremely close to the star, so like the rocky terrestrial planets in our solar system, like Mercury, Venus, and Earth, they would be too close to the star when it swells up as a red giant, and they will be totally engulfed and destroyed by the red giant at this stage. And then, as a planetary nebula, basically the outer layers of the star are basically expelled and are ejected throughout the galaxy then. And the other planets should, well, it depends all on the planets, but let's just say that they should survive this stage. But it's really when the star becomes a white dwarf that things start to become violent again, because white dwarfs have such high surface gravities. This can do something called tidal disruption to the planets. So this basically means that gravity is so strong from the white dwarf that it can break apart the surviving planets, and this basically turns it into planetary debris, which we call it, and planetesimals. So then this is the stuff that spirals into and accretes onto the white dwarf, which makes it metal polluted and is how we can then determine the composition of the evolved planetary systems. And what was your first question again? Sorry, I've forgotten it.
Yeah, can we detect when a star become a red giant?
Yes, we can. So that involves a bit of maths and physics equations. So it all depends on the mass and luminosity of the star, which are all you can work out all of those parameters. So then, yeah, you can figure out when it will become a red giant. So our sun will stay on the main sequence stage for another 5 billion years. No, 5 billion, yeah. And then it will become a red giant, and this is a fairly short stage. And then it will become a white dwarf in about 6 billion years.
Thank you.
You're welcome.
Yeah, thank you so much for those questions. Please raise your hand if you have more questions, everyone, or I'll just, um, take over and ask questions. So based on this data, would you be able to create like a model how our white dwarf would look like and the composition, or was it done, and is there a huge discrepancy? And then could you basically make a prediction into, the past and the future, how, white dwarfs would differ, and then how different solar systems, along the universe evolution would change?
Yeah, so we know when our sun will become a white dwarf, and we have a pretty good idea of what planets will survive. So we know that Mercury and Venus won't, they'll definitely be engulfed. Earth will probably be engulfed. There's still a bit of an open question about that. But then all the other planets will survive. But then they will be broken up and they will be accreted onto the white dwarf. And then it all depends on the time scales of those events to what the atmosphere of the white dwarf will look like. So if everything is accreted and broken up at the same time, then the planets, so Mars, Jupiter, Saturn, Uranus, Neptune, if they haven't been ejected, will accrete onto the our white dwarf sun. And the chemical composition of that will just be a mixture of the whole planetary system. But then, of course, you have to observe it at a particular time. So if you were lucky and you observed it at the start of the accretion, then you'd be able to see everything. If you observed it millions and millions of years afterwards, then the heavier elements will have sunk through the white dwarf and be undetectable, because with spectroscopy, that's just taking a spectra of the white dwarf atmosphere, so we can only see what's in the atmosphere. So if the metals have sunk through the atmosphere towards the core of the white dwarf, we won't be able to detect those, and then we wouldn't know what heavier elements were present. That being said, at the moment, we have observed lots of metal-polluted white dwarfs, albeit not quite as old as the ones in my study, but we've observed lots of metal-polluted white dwarfs in our galaxy, and we've got a pretty good idea of the general metals that are present in them. So that's why with our model atmospheres, we include some metals that we don't detect, but we just include very, very low abundances of them, because we can make a pretty good guess that they were there but they have just sunk through the white dwarf atmosphere by the time that we observe them. Does that answer your question?
Yeah, that's interesting. So you basically are looking at white dwarfs at different time points. So at different ones that are in different time points. That based on that you can make the predictions. That's really interesting. And then the other thing is, can it say anything like for sure it can, but about the universe evolution itself? And I don't know if that's a too personal question for a physicist, but do you believe in just, the bouncing back theory versus, there was one start and like a never ending, like, that could this research also give us more insight into, those big questions? And do you have an opinion on those theories? Thank you.
Yeah, sure. That's another interesting question. So, because of the mysterious chemical composition of WD J2147, which is the older white dwarf, that did make us think a little bit about the evolution of the universe, and it made us ask the question, how did so much lithium become present in the atmosphere of the white dwarf? Because there just shouldn't be. We don't know how it got there. So that's why we looked at something like primordial lithium enhancement, because lithium is produced around 30 minutes after the Big Bang. So the Big Bang was at the start of the universe, and that happened 13.8 billion years ago. So 30 minutes after the Big Bang, when the universe was 30 minutes old, it produced lithium. And there isn't really another way that it can be produced. So we're just not sure how our white dwarf got so lithium rich and potassium rich, because they sort of contradict each other, like that's shown in the slide with the grey tracks on, with the abundance ratio plots. So when we decrease the lithium in the white dwarfs and make it more like the lithium composition that we see in Earth, which is good, which is what we want. We want to make it more comparable to Earth. But when we do that, it increases the potassium abundance to ridiculously high values that we cannot explain. But when we, so if we go the other way and say, okay, we will keep the potassium abundance to what it is, to what we see now, but then the lithium abundance is far too high to explain. So, so with this white dwarf in particular, we did have to think about these bigger questions of what has happened in the universe to make these to give such rich chemical abundances of lithium and potassium to this white dwarf. So yeah, this is definitely a study that will help in this puzzle, because like in science, everything is just a building block to the next thing. So this will definitely help. Maybe not answer some fundamental questions about the universe, but it will definitely spark some questions, I would say, and provide some evidence on theories that are likely or unlikely.
Well, that is really interesting, and yeah, I hope you'll solve the puzzle. If I may make a health joke, I think the white dwarf went to the doctor and got some lithium for mental health and potassium for the heart. No, I'm joking because it's aging. Anyways, no, but that's really interesting, and I'm really looking forward to following that research and see what the explanation is. So I know we've been going now for an hour, so if anyone has some last comments and questions, please join us on stage. And yeah, do you think we'll solve the puzzle, or in your lifetime, our lifetime? I hope we
Oh,
do. Is there a way to simulate like our experimental physicists now doing experiments to try to see how that is possible?
yeah, so I hope it's going to be solved in my lifetime. But yeah, so this is a very hot topic at the moment. There are a few groups around the world working on this because looking at ultra cool white dwarfs like these ones, which are really old, this is really pushing the boundary of dense physics because these white dwarfs are so cool. Their atmospheres are really dense, so we have to model them as like a fluid, and basically this is really pushing current physics. So there is people working on like experimentally looking at really dense fluids and seeing how they behave. There are theoretical physicists modeling it and creating more physics, basically, to try and explain what's going on. And there are people like people in my team who are working on the models to really implement this really high density physics in our models. So I believe that we will get to the bottom of this mystery because there's so many people working on it and so many people want to know the answers because it's so interesting. So this is a really good study, really. It's very up to date, and so just watch this space for new results coming out.
Well, that's so exciting, and that you kind of contributed to eliciting this basically almost new field. It must be really exciting. And are there more white dwarfs around that age, basically, in that age class? And do they show similar characteristics? Like, is that like basically from that generation the characteristics of white dwarfs, or is this one a very special one?
So this is the oldest metal-polluted white dwarf we found. So there are older white dwarfs in the galaxy which do not have metal pollution. So what's special about WD J2147 from this study is that it's the oldest white dwarf in the galaxy with metal pollution. So this has got the oldest evolved planetary system that we found, which is really the key find here. And so far, this is the oldest one that we've found. There are others of similar age, which are the ones that I included in the DZ subsample in the paper. So the other white dwarf in this study, WD J1922, is around 9 gigayears old. There are others in the DZ subsample around 9.5 and 8 gigayears old. So there are some of similar ages, and work has been done in the literature on these, specifically basically just like this study, looking at their parameters, modeling them, and trying to work out their chemical abundance ratios and compare them to solar system benchmarks. But yeah, so there are other white dwarfs, and I would hazard a guess that there are more in the Milky Way, but these really old and cool white dwarfs are challenging to find, basically, because they're so faint, because they have been a white dwarf for so long, they've been cooling for so long, they're very faint, and they're especially faint compared to other stars. So you need a good telescope, basically, to observe them. So there are other white dwarfs that are similar to these two, and I would definitely be interested in searching for more.
Well, it's really interesting. And if they had electric vehicles, they were very they were very happy because they had a lot of resources for battery. I'm kidding. Like if there was life that generated batteries, they were very lucky. But probably not. So, but yeah, this is really exciting and so amazing, and we are so thankful for the time you shared here and the knowledge you shared. I learned so much. So good luck for your future research, and we'll be excited to follow your work. And yeah, we wish you all the best and a lot of grants, and we will follow the mystery with you.
Oh, thank you so much, and thank you for inviting me to speak today. It's been great.
Yes, thank you very much, Abigail and Katerina. Very interesting.
Well, thank you, and sorry for my really bad jokes, but yeah. Anyway, okay. And oh yeah, if you like discussions like this, follow the club. We'll have tomorrow Dr. Feldman's coming and talking about how breathing patterns can influence emotion. He has been studying this field for some time and has some really great publications on it. And yeah, thank you again. Thank you so much, Abigail. This was really amazing and exciting. And good luck with everything.
Thank you very much.
Close the room in 3, 2, 1. Bye, everyone. Thank you.